Hello, ladies and gentlemen. Welcome back to our fifth day of Chapter 5. We are now moving on to Section 5.3, What is Conditional Probability? By the end of this lesson, you will be able to calculate and interpret conditional probabilities, and I highly recommend that you try these problems when we are finished. Let's get started. As I said, we are on Section 5.3, Day 1, Conditional Probability. This example is one that we do in class, so look to your class materials for this work. Right. Now you can read much of this information on pages 358 to 365. Let's dive in. The probability of an event can change if we know that some other event has occurred. Flipping a coin and getting heads will not change the probability of getting heads nor tails in future flips of a coin. However, it does change the probability of getting certain outcomes that include the coin flip we already know the result of. For example, if you know that the first coin flip out of 2 is heads, the probability of getting 2 tails will be 0, regardless of how the second coin flip turns out, because we already got at least one result of heads. This idea that prior knowledge can change the probability of events is the key to many applications of probability. Right. Now, what is a conditional probability? Is there a formula, and is it on the formula sheet? So the definition, the probability that one event happens given that another event is known to have happened, is called a conditional probability. The conditional probability that event A happens given that event B has happened is denoted by probability of A given B. So we already know that event B happened. That's the condition that's placed on probability of event A. Yes, there's a formula, and yes, it's on the formula sheet. Here's your formula. So probability of A given B is the probability of A and B divided by the probability of B. Right? This can also be written using the symbolic notation, and that's basically the probability that both events occurred divided by the probability that the given event occurs. Now that should be event, not even. Right, so if yours is also messed up there, go ahead and write in that T. Now keep in mind this also means that the following is true. So probability of A given B, notice that we have the intersection then divided by B. Probability of B given A, again, probability of the intersection, but this time divided by the probability of A. We're always dividing by the probability of the event that was known, which is the second event in our notation. Now, how can you tell if 2 events are independent? So first we need to know our definition. A and B are independent if knowing whether or not one event occurred does not change the probability that the other event will happen. So in other words, events A and B are independent if the probability of A given B is equal to the probability of A given not B is equal to probability of A. So the probability of A stays the same regardless of whether or not we know that B happened or B did not happen. Now, alternatively, events A and B are independent if the probability of B stays the same, regardless of whether or not we know that A occurred or A did not occur. The probability of B should be the same throughout. Right, so let's try this. In the Diamondbacks example, so are the events T and W independent, and explain. So let's take a look at the table that we had from this one. So this one was getting free tacos given that the Diamondbacks had a win. So let's see, we have tacos, so probability of getting tacos would be 30 out of 81. That's just the general probability. Now, does the probability of getting tacos, getting free tacos, change depending on whether or not they won? So we're looking at 30 out of 81. Probability of getting tacos given that they won would be 26 out of 41. Probability of getting tacos given that they didn't win would be 4 out of 40. And when we go through and we calculate these events, so probability of tacos, just generally 30 out of 81. Tacos given they won, so we're looking out of the total wins, 26 times they got tacos. That's 0.63. Probability of tacos given that they didn't win, that happened 4 times out of 40. That's 0.1. So this 0.37 that we get from 30 out of 81 is different from this 0.63 and this 0.1. These are not the same. That means that these events are not independent because you are more likely to get free tacos if the Diamondbacks win than if they lose. This probability is higher than this one. And that's how you test for independence. Now, I also want us to fill in the two-way tables so that A and B are mutually exclusive. Now let me refresh your memory. Mutually exclusive events means that the intersection of A and B is 0. So if we look at A and B, their intersection, I have this marked down as 0 because that's what mutually exclusive means, right? They cannot occur at the same time. That means that the total times that A occurred didn't happen when B did not occur. The total times that B occurred happened when A did not occur. And there were 10 times that neither one happened. All right? So fill in that 0 first with the mutually exclusive and then fill in the rest. So I took 60 minus 0 is 60, 30 minus 0 is 30, and this 40 and 70 here, 40 minus 30 gives you 10, 70 minus 60 also gives you 10. Right? So we filled this in so that these two events are mutually exclusive. They cannot occur at the same time. Right? Fill in the two-way tables so that A and B are independent. Now, if they're independent, then that means that the probability of A given B needs to be the same as the probability of A. The probability of A given B is the probability of the intersection of A and B divided by the probability of B. Probability of A, 60 over 100 is 0.6. Probability of B, 30 over 100 is 0.3. So if I fill this in, probability of A would have to be the same. Probability of A given B would have to be the same as probability of A. So I went ahead and put that as 0.6. That's what independent means. These two aren't changing, so this can be put in its place. The intersection of A and B would then be divided by the probability of B, which is the 0.3. If I multiply this to the other side, I can solve for the probability of the intersection when they both occur. 0.3 times 0.6 gives me 0.18, which is 18 out of 100, which is why I have 18 filled in here. All right, A and B occurring, both of them, 18 out of 100 in order to keep this probability the same as this one. And once I have that 18, it's just a matter of subtracting in order to find the rest of the values. 60 minus 18 is 42, 30 minus 18 is 12, 40 minus 12 is 28. I could have also taken 70 minus 42 is 28. Now, just to remind you guys what the difference between mutually exclusive, in other words, disjoint, is from independent. Mutually exclusive events share no outcomes, which means probability of A and B is equal to 0. Independent events don't give information about the other event, so probability of A given B is the same as probability of A given not B is same as the probability of A. Same thing with the probability of B, no matter whether it's given that A occurred or A did not occur, probability of B should stay the same throughout. All right, try these problems and we'll see you in class.